Now we're actually talking about the confidence interval yesterday, and then just finish off on that, and then we're gonna take a look at the Excel project number 4 in a second, and we'll finish this. Um, if we're up to this. Okay. Yeah, so yesterday actually we went over this a little bit just on how to convert from the top formula to the bottom. So I'm going to do it one more time. So first of all, we will square both side equation. Square this side, square the other side. So after we square both sides, we get e squared equal to 3 equals e squared times square root square offset each other. P hat times q hat over simple size. And then now from here, so we're going to solve for m. So make a fraction here as e squared equal to e squared times q hat over sample size. And side will also make a fraction. And then once we cross multiply, we get e squared. And n goes to left. And 1 times equals z squared times p hat q hat. And after that, we divide both sides equation by e squared. Cancel the e squared, and n is by itself. Then we come out with this formula here. So that's how we actually estimate the sample size. So let's say in a given, let's say if you want to estimate the sample size, you can know the confidence level. And then, and also the margin error. And then we can estimate the sample size using this formula. So basically, for those most researchers, they will determine the sample size first, like before they start any analysis using this typical formula to do that. And also, if you look at it, when the sample size, let's say when the p hat is known, meaning if you can figure out the p hat from previous studies, or like if anybody have done a similar work in the past, then maybe you get a similar p hat, then you can use that. But when the p hat is unknown, then we are assuming both when this is unknown, right? Then we're assuming p hat equal to q hat equal to 0.5. And then this will guarantee we will end up with the largest sample size. And this is how you look at it, right? Now, this is actually a little bit of algebra. Okay, yeah, Caleb, any question?
Just a quick reminder for myself. Q hat is just 1 minus P hat. Is that correct?
Exactly, that's right.
Okay, thank you.
But, so Q hat actually is 1 minus P. And so the largest value for product of P hat and Q hat will be exactly what Caleb just mentioned. So if you're replacing Q hat with 1 minus P hat, And then if you distribute it, we're going to get p hat minus p hat squared. This is a lot like if you assuming p hat is x, right? This is like x minus x squared. We can do a little bit of transformation here, and then you get negative x squared plus x. And if you complete in a square, minus x will be minus half square plus a quarter. Then, as you can see, when x equal to half, actually this value here will reach the maximum of a quarter. So the maximum value actually it's a quarter. This is called a vertex for this. We call these quadratic functions, right? Vertex for the quadratic functions, and a vertex is either a maximum or minimum. In this case, it's a maximum. That's why this is 0.25. So the maximum value is 0.25 when x is p hat equal to half, right, which is 0.5. This is how you analyze this and figure out that when p hat is 0.5, then we'll guarantee we're going to have a larger sample size, right? And then the larger the sample size, the better it is. It's always guarantee a better result. Better result is. So that's basically if we're picking a bigger sample size with a simple random sample, then you always have a better result. So that's basically how you look at this. When p hat is unknown, right? And then a lot of times p hat is unknown. So we just using the 0.25 as a product of p hat times q hat. Any question about this? This is kind of like a quick proof why people is using 0.25. And then in this case, they are being conservative. Using 0.25 will guarantee the largest sample size. Right. And that's so running rules, right, for the sample size. Let's say you get sample size which is 100.111, right? And you're going to round up to next whole number 101. So the rounding rule is always run the decimal number to next whole number or next larger whole number. So if n equal to, let's say, you calculate that it's 100.0001, you're still going to run up to 101. This is basically the running rules. Always run up. So again, bigger the sample size, the result is slightly better. So this is running rules. And let's look at this, right? Many companies are interested in knowing the percentage of adults who buy clothing online. So all those e-commerce companies, they actually collect the data from the population, and they hire some firm or some company to work on this project. So how many adults must be surveyed in order to be 95% confidence? So basically the e-commerce company would tell their contractor, they want a 95% confidence or 99% confidence. And then the sample percentage is never known by no more than 3 percentage points. And this sentence indicates the maximum likely difference between the sample proportion and the population proportion is 3% point. 3%, so 3%. So they want to control the error rate within 3%. So not exceeding 3%. And use a recent result from the Census Bureau. 66% of adults buy clothing online. This is basically, we are given p hat here from the Census Bureau. So that's going to be 0.66. Assuming we have no possible value of the proportion, this is actually, the Census Bureau actually is population proportion, so it's a P. Because Census Bureau always collect the data from the entire population. So in this case, P is 0.66. And then the second one is assuming that we have no prior information suggesting a possible value of the proportion. So this thing is P hat is unknown. And then we want to figure out that we're going to estimate the sample size. In this case, so when P hat is unknown, so right here, first case, P is 0.66, and then we're assuming P hat is, because we know the population proportion, so sample proportion will be 0.66 as well. The second case is P hat is unknown, so basically covers two different scenarios. So for the first case, P hat is 0.66, Q hat is 0.34, 1 minus P hat. Alpha is 0.05, so the critical z-score is 1.96. And the margin error is 3%. So we are using the critical z-score where that's P hat, that's Q hat over margin error squared. So this is going to be 1.96 squared times 0.66 times 0.34 over margin error squared, 0.03 squared. And then we'll get, let's see, it will be 957 point something. And put into the calculator, let's see what that is, 0.66 times 0.34 over 0.03 squared. And this turned out to be maybe I can just show you in Excel. In Excel. So it's 1.96 squared times 166 times 0.34 over 0.03 squared. I will get 957.839. 957.839. So this is approximately, no, actually it's that value. But again, running rules run up the next whole number, so mathematically. So so the independent contractors need to conduct a survey, collect information from a simple random sample of 958 adults. In order to guarantee they have 95% confidence and the margin error is within 3 percentage points. And then the second part is when P hat is unknown. Here, P hat is unknown. And then the P hat, Q hat must be both. So P hat 0.5, Q hat equal 0.5. So the sample size is going to be equal to this score where times P hat 0.5, 0.5 times 0.5, 0.25. Over margin average. So this is 1.96 squared times 0.25 over 0.03 square. Now we're going to expect to have a larger sample size because using 0.5 will guarantee you have a larger sample size. One more time, 1.96 square times 0.25 over 103 square. Now we get this 1067.11. So it's much larger. It's 100 tenth. Right? It's sample size increased by 110. 1067.11. But again, we run up the next whole number. So 1068. So similar conclusion to be 95% confident that our sample percentage is within 3 percentage point of the true proportion for the entire population. We should obtain a simple random sample of 1068 adults. So that's basically how you estimate the sample size with the designated parameters. Any question about this? And the last part is you want to find a, let's say, given the confidence interval. Let's say given confidence interval system if you have minus margin error, large margin error. And then you want to find out, you want to figure out the p-hat and p-hat and margin error. So we could do this, right? So this is, so basically p-hat minus margin error, so we consider the lower limit. Lower confidence limit. And then p-hat plus margin error is considered upper confidence limit. You don't calculate the p-hat, so it's kind of like system of linear equations. You just add these two equations, right? So we'll cancel this margin error, so we're gonna get 2 p-hat twice a p-hat equal to lower class limit plus up class limit. Then we divide 2 from both side equation. You get p-hat equal to this. You see, this is exactly upper confidence limit plus lower confidence limit divided by 2. And that's how they calculate the p-hat. So by setting up the system of linear equation. And for margin error, you could do this. You can just subtract the second equation. So taking this p-hat plus margin error equal to upper confidence limit, and then p-hat minus margin error is lower confidence limit. Now if you subtract 2 equations, right, just like the subtracted p-hat will be cancelled. Then margin error minus negative margin error becomes margin error plus margin error. So we get 2e, twice of the margin error equal to upper confidence level minus lower level. Now divide both sides of the equation by 2. The margin error equal to upper confidence limit of minus lower confidence limit divided by 2. And this is basically why they come up with these two, how they come up with these two formulas. Any question about this? So for example, as I say, we have a confidence interval, it's just going to be 0.26 and then 0.64. And then so the p-hat here will be adding these two numbers 0.26 plus 0.64 divided by 2. Using upper limit, upper confidence limit, adding lower confidence limit divided by 2. So this is 0.92. So it's 0.45. And then the margin error, it's 0.64 minus 0.26 divided by 2. This is 0.38 by 2. So it's 0.19. So you can also convert this as 0.45 plus minus 0.19. So p-hat plus minus margin error. This is how we apply these formulas to figure out the p-hat margin error. Now let's go back to the Brightspace, I mean the Lumen, let's work on some exercise in this section. Power. So we complete the confidence interval to estimate the population proportion. So that's an exercise here. One practice. Okay. Let's look at the first question here. So in the recent poll, 510 people were asked if they like dogs, and 70% said they did. Find the margin error of this poll. That's 99% confidence level. Yeah, so maybe let me just open my formula sheet. I'll give you a couple minutes and then you guys can try this. Just open it on the side.
When we give the final answer, is that assuming plus or minus?
This one, we just do the margin error, right? We don't need to construct the confidence interval, just margin error.
Do you want us to answer or do you want to go over it?
Sure, I go over this. Sure, yeah. Caleb, maybe you can try.
I got 0.0523 because your n is 510, your p hat is 0.7. And then the z score for a 99% confidence level is 2.576.
Yeah,
Um,
575, right? Yeah, yeah.
oh yeah, five
Uh,
five. Yeah,
yeah. So if you're using Excel, it'll be 2.576. Probably
yeah.
that's somewhere
That's
close. Yeah.
and then
Mhm.
you plug everything into the equation for E. Um,
Exactly. So zero point 0.7. So Q has zero point 0.3. So the margin error here is 3 equals Z score. I so P hat times Q hat over sample size. It's 2.575 times radical zero point 0.7 times zero point 0.3 over 510. I'm going to run it to three decimal place. So I'm going to show you Excel. Yes, it's going to go this one 2 point. If you want to get the triple Z score from the Excel is going to be this around that. As the IMV, I'm going to go over this later when we work on the Excel project number 3. But in this case, it's going to be 1 minus 1% by 2. Because on both tails, left tail, right tail, occupy 1% divided by 2, that's area on the right tail. So 1 minus that will be accumulated area from the left. Can we get
out
this,
of
right? Mm-hmm.
out of curiosity, because I did this in Excel. So my
Mm-hmm.
husband taught me how to do this yesterday. Why does the Z-score round up in Excel versus what it actually is in
Oh,
the part?
oh, so the Excel usually give us, so we can have as many decimal as possible. But if
Oh, I
you
see.
perform the actual, if you're doing the actual project, let's say doing the real project, or any like, uh, you should use this number, right? Like as many decimal as possible. It should guarantee that your result is more accurate. So you should use this instead.
Got it.
Yeah. But since you are using the table A2 for final, so it's going to stick with the numbers from the table A2. So it's going to be 2.575 times square root p hat, which is zero point 0.7 times zero point 0.3 over 510. And that gives us this. Now we want 3 decimal place. Down to 3 decimal place. So the 0.052. So the answer is 0.052. Yep, it's a good answer. Yeah. Now let's look at this one. Question 2. Sample size p hat construct a 95% confidence interval. 3 decimal place for the answer. Yeah, give it a couple minutes. I'll go over the solution in a bit. over this, but again, we are given p hat, so q hat is given as well, so 0.6. And 95% confidence, so the critical z-score is 1.96. Now we find a margin error first. Margin error is critical z-score and p hat. It's q hat over sample size. That's 1.96 and square root of 0.6 times 0.4 over 420. And we will run this to 3 decimal place. Let me just do the calculation. So minus 6 square root 0.6.4 over 420. That will do it. And then 3 decimal place. It's 0.047. So we find a margin error that's approximately 0.047. Now we construct the 95% confidence interval. It will be p hat minus margin error, q plus margin error. And then this is going to be 0.4 minus 0.047, 0.4 plus 0.047. So our lower confidence limit is 0.353. Upper confidence limit is 0.4%. So any question about this? It's all good. Okay. Now let's look at this, right? Question 3, out of 600 people sampled, 430 had kids. Based on this, construct a 95% confidence interval for the true proportion people with kids. Let's look at the solution. So here the p-hat is not explicitly given here. So we have binary outcomes, either having kids or not having kids. So having kids is a success event. So we get the number of successes of 438, and then out of 600 people, so the p-hat is going to be x over n, x amount of successes. This context is 438 over 600. And we divide into that, I think it's 172, right? 438 over 600. Yeah, 0.73. So 0.73, that's the p-hat, meaning 73% of the people have kids. And so q-hat is going to be complement minus p-hat. So 1 minus 0.73, it's 0.27. And then 95% confidence equals z-score, it's 1.96. And then so first thing we will find out in the sample size as well. Sample size is find out margin error first. Here margin error equal z-score over square root q-hat for sample size. So this is going to be 1.96 times square root of 0.73 times 0.27 over 600. And that's 3 decimal place. So let's get the decimal result. 1.96 times square root 0.73 times 0.27 over 600. And if you enter, we get a result, E 0.036. When we run it to 3 decimal place, 0.036. Margin error is 0.036, about 3.6 percentage point. And then we take in the p-hat and margin error. So this is 95% of the level. So 0.73 and 0.036. 0.73 plus 0.036. And so the difference for the first one is the difference 0.694. That's the lower limit, which is 69.4%. Upper limit, it's 0.766. 76.6%. So you can say that at least 69% of the people have kids, right, with 95% confidence for the entire population. Any question about this? Point 694, 0.766. Okay. Yeah, the both good, right? Now let's look at this question. A political candidate asked you to conduct the poll. So all those politicians, right? They usually that's why they need fundings, right? We look at the crowdfundings or fundings from the different companies so they can fund their campaign, right? And this is an important part of the campaign is figure out percent of people who support that particular candidate. So if the candidate only won 10% of margin error at a 95% confidence level, what size of sample is needed? Okay. You guys try this quickly. Let's go with this one. So this one is estimating the size, right? Sample size. So sample size is what we are looking for. And we have margin error here. We explicitly indicated 1% error. So it's going wrong. And also 95% confidence equals z-score is 1.96. So and then p hat, q hat unknown, right? Because maybe this candidate just took over the job, right? Like Governor Hochul, right? She took over the job in the middle of the middle of term, right? So she probably have no idea, what percent of people who support her. When we took over the office, governor's office post. So this is exactly will fit her scenario. So if she want to run for the next, governor campaign, then this is something to consider. So the sample size, so p hat, q hat unknown, p hat is unknown. So we're assuming p hat equals q hat. The sample size equals z-score square. That's p hat, q hat, which is 25 over margin error squared. It's 1.96 squared times 0.25 over 0.1 squared. And we put into the Excel. So it's 1.96 squared times 0.25 over 0.1 squared. So 96, my sample 96, 96.04. And then we will run up to next whole number. So run up to 97. So the sample of 97 people should be accomplished. He or she will accomplish this goal, right? With the 10% of margin error, with 95% confidence. And so let's say if we want to improve improve the margin error, maybe reduce to 1%, right? Hypothetically speaking, right? If the margin error is 1%, and then this is a hypothetical scenario, and then 99% confidence. Now the sample size will be much bigger, right? So if you look at it, critical z-score now is 2.575, and the margin error is 0.01. So the sample size is going to be 2.575 squared, 0.25 over 0.01 squared. Then you see this big improvement, right? Because it's narrowed down it's kind of like a shrinking the margin error, also having a bigger confidence. Let's see how large that sample is. So 2.575 squared times 0.25 over 0.01 squared. Yes, now it's so much bigger, right? It will be 16,577, right? That amount of so this is kind of like a lot bigger sample size, right? This definitely requires a very professional service. As you can see, so this 16,577 compared to just 97. So you change the parameters slightly, then all the remaining things changes, right? Like sample size definitely go up significantly. Any question about this? Okay, so it's going to be 97 for this uh, for this condition. Yeah. Now let's look at this. Question 5. Insurance company are interested in knowing the population percentage of drivers who always buckle up before riding the car. They randomly survey 407 drivers, and found that 319 claim to always buckle up. Construct an 80% confidence interval for the population proportion that claim to always buckle up. Now it's 80% confidence, right? This is something we haven't deal with yet, but maybe you try first. All right, let's go over this. So start with the 80% confidence. So we draw the bell curve. And basically, its middle section is 80%. So each tail would occupy 10%, out of 20%. We are looking for this preposition. You combine the 80 and the 10%, that's going to be the area to the left. So 90%, a total 90%. And so based on 90%, we can look for critical z-score. So let's go back to table A2. It's 0.9000. We don't have exact match. And this one is the closest, 0.8997. So that gives us 1.28. So 0.8997, that'll be the best match in the table A2. So the critical z-score is 1.28. And also, we know the sample size is 407 drivers, 319 buckle up. So the p-hat here is going to be absolute n. Buckling up is considered as a success event, right? For insurance company, not buckling up will be the failure event. You do 319 over 407. That will give us p-hat, 319. Over 407. I'm going to keep more decimal place this time. Let me see if any instruction here, how many decimal we should keep. Not 3 decimal place, but for p-hat, I think we should keep more decimal place in order to keep the accuracy, keep it accurate. So going back here, so take 0.78, 378, right, at least 5. So I take 0.78, 378. So we know p-hat and q-hat will be complement. P-hat. This is going to be 0.21622. And we know both p-hat, q-hat, and we can find the margin error. Critical z-score, p-hat, q-hat sample size. So margin error equal to critical z-score p-hat, q-hat, sample size. So this is 1.28 times the root of 0.78378 times 0.2163 over 407. This time we can run it to 3 decimal because it's approaching the final step. So it should be good. So 1.28 times square root of 0.78378 times 0.21623. And over sample size 407. And then we get this, right? So it's 0.026. We run it 3 decimal place. 0.026. Now the 80% confidence interval, 80% confidence interval, it's going to be p hat minus nothing ever p hat plus nothing. And so we get 0.7, so 3 decimal 0.784 minus 0.026 and 0.784 plus 0.026. And the difference, let's see the difference is 0.758. And then the upper limit, 0.830. No, actually, yeah, it's 0.810. Yeah, 810. So that's going to be the 80% confidence interval. So 0.758, 0.810. So they want to complete 758 and 0.81. So they do want to put in this, put in the interval form. 0.810. Was that submitted? It's a correct answer. Okay. Any question about this? Yeah, this one is not. This one should be on the second part. Okay, about population mean. Don't worry about this. We'll do this on Monday. Okay. So now okay, that will be all the exercise for part one about population proportion. And then we're gonna move on to the Excel project number 4. So let's go back to course home and then go down to Excel demo. And then we take the lab 4 practice. So open this file here, lab 4 practice, download the file. Now go back here. So this one is just applying what we learned, right? In chapter 6 about the normal distribution and central limit theorem to solve some problems. So first one is question 1. Find the percentage of data in the standard normal curve to the left of the z-score equal to minus 0.65. So the formula we are using here is, because it's given a z-score, so this is standard normal distribution. And also, so this formula is standard normal distribution. It says returning the standard normal distribution with the mean 0, standard deviation 1. And I open parentheses, and then put in the z-score. So it will be minus 0.65. And the thing is, we are looking for the area to the left because it says left right here. So we are accumulating everything to the left. So putting true. Close parentheses. And that will do it. And then if you enter, you get a result, right? With this, but we can run to 4 decimal place. Yes. We can format a little bit. Four decimal. Be consistent with the table A2. And then second one is find the area to the right of z-score equal to 0.95. Now this one, it's area to the right. So you do 1 minus area to the left. So again, lambda s dot dist, and then putting 0.95. And then we are accumulating everything to the left. Close parentheses. So the second part, this part is actually area to the left. And 1 minus that gives us area to the right. So that will hit enter. You get the result. And then the third one is area in between these two z-scores. So we put in bigger, same formula, bigger z-score first, 1.78, through accumulating everything to the left, minus lambda s dot dist, smaller z-score 0.73, true. And then once we hit enter, we will get the results. Right, enter, get 0.1952. Now you guys try part D. It's similar to the one we just did, right? Area in between. All right, so let's check it. Put equal sign, lambda s dot dist, putting 1.95 first, bigger z-score gives us the area, and minus, same formula, minus is negative 1.75. We're not looking for the Pauli density function. We are accumulating area to the left. I'm going to enter this. Any question about this? Now let's look at this question 2. Suppose IQ score, right? Have a normal distribution with a mean 105, standard deviation 80. Find the percentage of the individuals with IQ score above 124, above 92, below 85, between 74 and 119. Right. So above 124, so it will be this. So we're using this formula, right? So dot dist. So basically just normal distribution and then putting x values, but because of the above, right? So it'll be 1 minus. This formula will always give us the area to the left. If you want the area to the right, then you do 1 minus area to the left. And putting x value 124, mean 105, standard deviation 18, we are accumulating everything to the left. Now, once we do that, we'll get the result. Hit enter. That is. So one more time. I'm going to format this. Okay. Now you try the second one, about 92. So the second one, very similar. We do 1 minus VST 92 and mean 105, standard deviation 18, coming to the left-hand side, putting true, and then he enter the result. So then below 85, it's just going to be lambda st. 85, area to the left, mean 105, standard deviation 18, true. And that will do it. It's 0.1333. And then the part D is between 74 and then 119. So we do area between, putting the bigger x value first, 108, 105, 18, true. Minus smaller area coming from the smaller x value 74. So minus lambda BIST 74, 105, 18, true. And that will give us the result. And this turned out to be 0.7391. This is the area in between. That, any question about question 2? Let's look at question 3. And this one, it's a supposed height of male students has normal distribution with a mean of 65 inches, standard deviation of 8 inches. Find height of male students among top 10%, bottom 10%. So the way how we look at it, top 10%, meaning we're separating the bottom 90% from the top 10%. So area to the left, it's going to be 90%. So you do lambda inverse, IMV, right? This means inverse of the normal distribution. Now we put in the probability, which is area to the left, it's 1 minus 10%. And then the mean is 65, standard deviation 8, and then close parentheses. And once we do that, then we get a result. If you enter, right, so it's about 75, 25. I'll just format this to 2 decimal place, 75.25 inches. And then bottom 10%, so it'll be equal to lambda inverse, right? Inverse of the normal distribution, right? Given the probability, and we try to find out the x values. So it's going to be 10%. Mean of 65, standard deviation of 8. Then key enter, you get this. Now the top 15%, it's going to be so lambda IMV probability area to the left, it's 1 minus 15%. The mean of 65 and standard deviation of 8. Okay. And so again, area to the left, it's 85%. Now if you enter, we get this 73.29 inches. And the bottom 15% on the IMB, and it's going to be 15%. Area to the left, 15%, 65, and 8. And he enter, you get that. And we can also try, let's try middle 90%. Let's say we haven't tried this, but Just gonna, one sec. Create another one, which is gonna be between middle 90%. So we call this E and hide male students among the middle 90%. And so basically this one, we're gonna have two values. So the bigger value, for the bigger value, because the middle 90%, so meaning each tail will have 5%. Maybe let me just quickly show you. Look at the middle 90%. It's 90%. So on each tail, that's 5%. And we want to know the z-score here, and then now looking for the z-score. Actually, just look for the x values. X value here and x value here. And for the bigger height, right, on the right side, the area is going to be 95%. And then for the smaller one, it's just going to be 5%. So go back here to Excel. So for the bigger one, we do lambda b, and an area for the bigger height, it's going to be, you can do 90% plus 5%, so 95%. Mean of 65, standard deviation of 8. That'll be the bigger height on the right side, on the right tail. And for the smaller height on the left tail, we are using 5%. Again, 5%. So it'll be lambda and b, and then we are using 5%. 65, 8. Basically, this will give us the smaller height. So, any question about this? So we will take a 20 minutes break. And then after we come back from the break, you guys, I'll give it 20 minutes, finish the Excel project number 4, and I will do some R demo. We'll do some coding in terms of the normal distribution. Okay. So your actual project is in the white space. Go down to Excel project submission, right? Problem number 4. Yeah, I'll talk to you guys in 20 minutes.